Welcome back to the lectures on chemistry with introduction to molecular spectroscopy. This lecture session is to help you with problem solving ability and also to think about how to organize your thought process when a set of data are given and you are asked to find the solution. Problem solving is an important part of learning, but it is not the only part. Okay. It is important for you to listen to lectures, it is important for you to read and understand things, discuss them with your friends and your teachers, but then use these problem sets to give you confidence that you have understood the material, understood within quotes that material with a reasonable degree of confidence. Okay. So, in this set of problems that we have 10 problems. The first problem is requiring you to identify which molecules have pure rotational, that is microwave spectrum, and which molecules have infrared spectrum, or the molecules which have both of them, and you are asked to identify them accordingly. The important point is, for a molecule to have a pure rotational or a microwave spectrum, the molecule should have a permanent dipole moment in its equilibrium geometry or in its equilibrium configuration. For a molecule to have infrared spectrum, during the vibrational motion, the dipole moment must change. The dipole moment need not be there to start with, but if in the process of vibrational motion the dipoles are created and destroyed, what you see is that that kind of a motion leads to an oscillation of the electric dipole moment, and such molecules will have infrared spectrum. Okay. So, obviously molecules which have a permanent dipole moment will all have an infrared spectrum. There is no question about that, because during the molecular motion during at least some of these motion, the dipole moment will change as the molecule vibrates and so on. So, let us take the first example, carbon monoxide. Carbon monoxide has a strong dipole moment, therefore, it has both microwave and IR spectrum. It has CO, both microwave and IR spectrum. The next one is CH2Cl2. This is a tetrahedral molecule and it has a permanent dipole moment due to the CCl bond having an electric dipole differently from that of the CH2, and therefore, this molecule also has both microwave spectrum and infrared spectrum. Carbon dioxide, which is the third one. Carbon dioxide does not have an electric dipole moment in its equilibrium geometry, therefore, it does not have a microwave spectrum, but it has two motions, the bending degrees of freedom and the asymmetric stretch. In both these normal modes of vibration, the molecule has a changing dipole moment, therefore, it has the infrared spectrum for these two degrees of freedom. The bending mode is doubly degenerate, therefore, you have degeneracy involved, but there are two frequencies, one for the bending mode and one for the asymmetric stretch. The molecule ammonia is pyramidal, has a dipole moment, therefore, it has both microwave spectrum and infrared spectrum. The molecule formaldehyde, acetaldehyde, CH3CHO, not formaldehyde, acetaldehyde, yes, it has a dipole moment, therefore, there are vibrational motions where the dipole will change during the vibration, giving rise to both IR and microwave spectrum. Methane is a perfect tetrahedron, and in its tetrahedral geometry the electric dipoles add to cancel each other, and therefore methane does not have a microwave spectrum, but methane has vibrational motion. Please remember it is a 5 atom molecule, therefore it has 3n minus 6 normal modes, which is 9 normal modes. Some of these normal modes lead to change in the dipole moment, therefore it has infrared spectrum. The symmetric stretch of CH4 will not have a dipole moment because all 4 hydrogen atoms vibrate away from equilibrium and all 4 go into that. Such modes are not seen, but in general it has IR spectrum. Benzene, the same thing. Benzene in its equilibrium structure does not have a dipole moment, therefore it is not microwave active. So, I will write microwave active here, and this is infrared active here. So, benzene does not have a microwave spectrum, but it has many degrees of freedom which lead to IR spectrum. Trans dichloroethane, ethylene. So, that is Cl, C, double bond C, H, Cl, H. This is given so that there is no equilibrium dipole moment. Therefore, this does not have a microwave spectrum, but it has IR spectrum. Ozone. Despite all the 3 oxygens involved, please remember ozone is an asymmetric top, and this oxygen is differently bonded to the other 2 oxygen. Therefore, asymmetric top has, and this molecule also has dipole moments, therefore it is microwave and IR active. IR active. Okay. Acetylene. It's quite clear that there is no dipole moment for this linear molecule. This molecule has a center of symmetry, therefore it is not microwave active, that is microwave inactive, but it has vibrational motions, therefore it is IR active. Hydrogen peroxide is a non-planar structure, bending structure. And therefore, it is a non-planar structure, therefore it has a dipole moment, therefore it is microwave active and IR active. And the last is propane, CH3, C triple bond CH. So, this has the asymmetric group CH3 here, therefore it is both microwave active and IR active. Okay. So, one has to look for the equilibrium geometry of the molecule and look for all its possible normal modes in determining which of them are IR active and which of them are microwave active and so on. So, let us go to the second problem. This is an interesting elementary though problem on the determination of the moment of inertia of water molecule about its symmetry axis. The symmetry axis of course passes through oxygen and it bisects the HOH bonds. So, the OH bond distance is given to you as 95.7 picometers and the HOH bond angle is also given as 104.5 degrees. So, the moment of inertia, if you recall, for water molecule, if you have to calculate about the symmetry axis, this is the symmetry axis, the C2 symmetry axis. Okay. And since on the C2 axis the oxygen resides, the oxygen does not contribute to the Mi Ri square term. Ri is 0 for the oxygen because it is on the axis. However, the hydrogens are at this distance which is perpendicular from the axis, it is a perpendicular distance that you have to take into account, and therefore you have a mass of hydrogen, and since this angle is given as 104.5 degrees, the half angle is 52.25 degrees and the bond length is given as 95.7 picometers. Therefore, it is easy for you to calculate this distance as Ri as 95.7. So, this is sine 52.25. Okay, that is the Ri. Therefore, two hydrogen atoms contribute to the overall moment of inertia for this molecule. Therefore, this is this value, and since it is a symmetry axis that we are talking about, the hydrogen atom on this side is also R1 and R2 are both equal. Therefore, what you have is 2mh times 95.7 into 10 raised to minus 12 meter square times sine square 52.25, and this is kilogram that you have to use. Therefore, you will have the moment of inertia I in terms of kilogram meter square. I think the numbers can be calculated by you. Therefore, let me not write that here. Okay. Let us go to the next problem. The next problem is about the fundamental vibrational frequency of hydrogen molecule and how it is related to the vibrational frequency of its isotopic substituents, the Hd, in which one hydrogen atom is substituted by the deuterium, and D2, in which both the atoms are replaced by deuterium. And one assumes that in these three species, the chemical nature, namely the force constant, which contributes to the bond strength of these three molecules, do not change by much. It is in that limit, how are these vibrational frequencies related to each other? This is again, it is a very simple problem to look at, because you know vibrational frequency for problem 3, vibrational frequency is related to the force constant and the mass of the molecule, that is the center mass, the reduced mass mu. This is the expression. Therefore, if you are writing nu H2, it is mu of H2, and K of H2 does not change from K of Hd, which is now obviously related to the mu of Hd by the same relation mu Hd, and nu of D2 is given by 1 by 2 pi square root of K mu D2. Therefore, if you know this number as 4401.2 centimeter inverse, then you can calculate where should the nu Hd should be by taking the ratio of this, namely nu Hd divided by nu H2 will turn out to be 1 by, because the k's will cancel, the 2 pi's will cancel, you will have 1 by square root, or let me write the final form, the square root of is Hd. Therefore, it is mu of H2 divided by mu of Hd. They are inversely proportional to the square, therefore, the ratio is that. And mu of H2 is easy to calculate if you assume H2 to be the H atomic mass as 1.008 AMU. If you multiply that by 1.661 into 10 raised to minus 27 kilograms, that is the amount for 1 AMU, that is a mass of 1 AMU associated with that. Then H2 is the reduced mass is nothing but 1.008 divided by 2.016 times 1.661 times 10 to the minus 27 kilograms. This is the mu of H2. And likewise, the mu of Hd, if you want to do that, please remember the relation is m1 m2 by m1 plus m2. Okay. So, for mu of Hd, the d is, I believe, 2.014. So, H is 1.008 times 1.661 times 10 to the minus 27 kilograms, and the d is 2.014 times 1.661 661 times 10 to the minus 27 kilograms. Therefore, the mu of Hd can be calculated as 1.008 times 2.014 divided by 3.022, the sum of the two, times 1.661 into 10 raised to minus 27. So, this is the mu of Hd. So, you can see that if you substitute the mu of Hd, the mu of Hd is slightly more than the mu of H2, and therefore, the square root of this number tells you that the nu of Hd is a little less than the nu of H2. Now, it is the same thing that you have to do for D2. For D2, you would use 2.014 times 2.014 divided by 4.028 times 10 to the minus 27 into 1.661 kilograms. Therefore, the mu of D2 is given by this number. Then you can calculate mu of H2, the nu of H2, the frequency of H2 divided by the frequency of D2 is the square root of the mu of D2 divided by the mu of H2. Okay. So, these are simple manipulations of the harmonic oscillator frequencies and also the isotopic concepts that vibrational and rotational frequencies do depend on the isotopic mass of the individual atoms. Okay. Then the fourth problem is on the Morse potential, and you recall the Morse potential expression which is given as V of R, the potential energy, and it is given by the factor D, which is the dissociation constant, times 1 minus e to the minus alpha or minus Re. Re is the equilibrium distance, R is the distance during the vibration. Therefore, this is the potential term that you would use to solve for the Morse oscillator Hamiltonian. The kinetic energy of the Morse oscillator is already given by p square by 2m, and this is the Vr, and therefore, you use this to solve the potential energy. Now, the question is, show that in the limit of small displacement, that is when R minus Re is very, very small, that this is the same as the harmonic oscillator approximation, and identify the harmonic frequency. Also, show that the asymptotic value is D. What are the interpretations for the parameters for the Morse potential? Okay. So, first of all, V of R is D times 1 minus e to the minus R minus Re times alpha whole square. Okay. So, suppose for R minus Re times alpha much less than 1, it is easy for us to expand this by writing D 1 minus, please remember exponential of minus Ax, when Ax is much less than 1, it is 1 minus Ax plus A square x square by 2 minus and so on. We are looking at small values of this, therefore, we stop with that. So, what you have is D is equal to 1 minus R minus Re alpha, and also there is a 1, okay, plus 1, because the exponential has 1 minus that. So, if we stop with that term, just the first term, and take the square of this term, which is already a very small one, we do not even go to the second term, then what you see is it is D into R minus Re whole square. And please remember, this is the potential energy form, and for the harmonic oscillator the potential energy form is half k x square, or in the notation of R minus Re it is half k R minus Re whole square. Okay. Therefore, you see that the alpha, there is an alpha here, therefore, there is an alpha square. Okay. So, D times R minus Re square times alpha square is approximately the potential V of R for small values of or about Re. So, what you have is d alpha square is equal to half k, and therefore, alpha is given as square root of k by 2 d. Okay. So, this is the Morse oscillator parameter, and please remember the Morse oscillator parameter has a dimension of 1 by the length, and k has the dimension of mass into this is the force constant, therefore, it is mass t to the minus 2, and this is energy, which is mass into length square into t to the minus 2, therefore, the square root of this is 1 by length. Okay. So, the interpretation of alpha is that this k, the force constant, is basically 2d alpha square. Okay. Now, the next question is, what is the harmonic frequency? Please remember, the harmonic frequency is 1 by 2 pi into square root of k by m, k by mu. And for the Morse oscillator, we just now found out that k is given by 2d alpha square. Therefore, the Morse oscillator frequency in the harmonic limit will be 1 by 2 pi square root of 2d, sorry, this is alpha square, not subscript, 2d alpha square, therefore 2d alpha square by mu. Okay. So, the Morse parameters d and alpha and the reduced mass of the molecule are used to define the harmonic frequency in the limit of small approximation. And second question in that is, show that the asymptotic value of Vr is d. Now, try to plot Vr as a function of r minus Re. Okay. It is d 1 minus e to the minus alpha r minus Re whole square. Okay. At r is equal to Re, the exponential has 0 exponent, and therefore it is 1, and therefore 1 minus 1 is 0. So, the V of r is 0. This is V of r. Okay. Therefore, V of r is 0 at r is equal to Re. Okay. For all values of r greater than Re, this number is smaller than 1, and therefore, this number is positive. 1 minus e to the minus alpha r minus Re whole square is positive, and since this keeps on becoming, this becomes smaller and smaller, what happens is this keeps on increasing until it reaches the maximum value of a d. When r minus Re is so large that this exponent is almost 0, because it is exponential of minus alpha x, and if x is very, very large, then the exponential of minus alpha x goes to 0. Therefore, you see that the V r reaches an asymptotic value, and this is the asymptote. Therefore, the d is the value for infinitely large Re or r compared to Re, and when r is less than Re, please remember this is negative, and therefore, the exponential is a positive, it has a positive exponent, therefore, the exponential increases, and this is a square. So, 1 minus this is negative, but the square of this is still increasing. Therefore, you see this increases very, very quickly, very, very steeply. This is the shape of the Morse potential, in which the d is the dissociation energy from equilibrium. You cannot measure d, you can only measure dissociation energy from the 0 point energy experimentally. 0 point energy will be the first V is equal to 0 state, and that will still have some energy, namely half h nu, if you remember that, the nu being the harmonic frequency, and therefore this number in Morse oscillator is called dE, dissociation energy from equilibrium, but the experimental values are d naught, which is this number from 0 point energy, that is d naught. Okay. So, this is how interpretation for the Morse potentials are given for their parameters. So, let me stop here for a moment and we will continue with the remaining 5 or 6 problems in the next part of this video.